So through this lecture, we are going to have some co-exploration on the topic, second law of thermodynamics and its application. So as per our syllabus, it's coming under Unit 2. So the following are the list of contents, what we are going to share, what we are going to explore together, starting from the need for second law of thermodynamics by understanding its limitation of first law of thermodynamics, followed by cyclic heat engine, Carnot cycle, a reversed Carnot cycle, Carnot's theorem, statement of second law and their equivalence, reversible and irreversible process, causes of irreversibility, Clausius theorem, concept of entropy, followed by entropy generation in closed system, at last concept of availability. So myself Sridharan, associate professor from the Department of Mechanical Engineering, SRMIST Tiruchirappalli. I welcome you all warmly to this wonderful co-exploration. Yeah. So this is the very first slide, as I mentioned earlier, which presents the limitations of first law of thermodynamics. In a nutshell, first law permits better understanding of complete conversion of heat into work. We all know at the input we use to supply heat, at the output we use to expect some work done, right? But first law of thermodynamics won't specify some limitations. Say, for example, on inferring the first law of thermodynamics, an amateur can understand even 100% is possible in a cyclic engine, right? But it is definitely impossible. That can be understood by a candidate, that is amateur candidate, only on exploring the concepts of second law of thermodynamics. In a nutshell, the term efficiency is introduced into the thermodynamic concepts only by the second law of thermodynamics. So this slide highlights what kind of concepts are there, and they're explained by first law, and why there is a need for second law of thermodynamics. So the first law of thermodynamics establishes equivalence between the quantity of heat used and the mechanical work, but does not specify the conditions, that is, the limitations, under which conversion of heat into work is possible, neither the direction in which the heat transfer can take place, right? So this gap has been bridged by the second law of thermodynamics. These are all the list of key statements of second law of thermodynamics. We used to have the uh, statements even from our childhood schooling itself, right? There are two statements. One is Clausius and the Kelvin Planck statement. As we witnessed earlier in the previous slide, these statements, right, specifies 100% conversion is impossible, not only in a heat engine, whatever may be the thermal system we are dealing with, right? So such kind of statement it was. The very first is the Clausius statement. It is impossible for a self-acting machine working in a cyclic process unaided by any external agency to convey heat from a body at a low temperature to a body at a high temperature. Or in a simply other words, heat on its own cannot flow from a colder to hotter body. As we all witnessed in the discussion of the very first unit itself, heat transfer or a heat flow always takes place naturally between high temperature and a low temperature, while cold to hot temperature is also possible, but with the help of some external work supplied to the system. So most of the community, that may be a commercial community or a domestic community, used to expect work done by the system. But here, in case of transferring heat between a colder body to hotter body, we used to perform some work done, thereby which we are able to convert, we are able to transfer heat from a cold body to a hot body. Then comes the Kelvin-Planck statement. It is impossible to construct an engine. Predominantly, these statements are presented in terms of heat engine. So only on understanding uh, some fundamental heat transfer happening within the engines, we can apply or extend the same towards the rest of thermal based systems, right? So predominantly we are going to have discussion based on engines, but anyhow, I will help you to understand the things in a detailed manner. So it is impossible to construct an engine which operating in a cycle produces no other effect except to extract heat from a single reservoir to do equivalent amount of work. One may understand these statements or one may not, right? So I presented the same in the form of a nutshell. Heat cannot spontaneously flow from a colder body to a hotter body without external work, as we discussed earlier. Kelvin Planck statement states no heat engine can convert all the heat absorbed from a single reservoir completely into work. So, one on understanding first law of thermodynamics may have an assumption that we are able to convert all the provided heat supplied at the input into work done. But it's definitely not. That is the key agenda of these two statements of second law. Then comes the key thermodynamic system. What are they? Starting from heat engine. A reversed heat engine includes two classifications, namely a refrigerator and a heat pump, right? So, as I mentioned earlier, we are going to have better understanding of heat engine first. Simply on understanding the working principle of heat engine, we can have it's a reverse in the name of refrigerator as well as heat pump. Yeah, for better understanding, just imagine in case of a conventional car engine, we used to supply some heat by combusting a fuel that may be a petrol or a diesel, right? What we are expecting? We are expecting work done at the output. That is given by the thermal efficiency of heat engine formula here. So a heat engine is a device which produces work done for the supplied amount of heat. But one thing you want to understand, we are not converting all the supplied heat into work done, right? This is for better understanding of the efficiency alone. Or in other words, we can say efficiency won't never been greater than 100 percentage. That is, if it is equal to 100 percentage now, we are obtaining complete work done for the total volume of the heat supplied, right? But it's not happen in the day-to-day activity. That can also be witnessed in many day-to-day application. As we are having this example repeatedly during our class session. For the consumed amount of fuels, say for example, while we are playing in a cricket ground, we can consume almost 1.5 liters of water, or only 2 liters, or that may vary from a body to body, right? Depending upon the draught of your throat concern, right? You can't going to convert those inputs into an effective work done, right? So that is stated by the second law of thermodynamics. Then coming to the second class of heat engine and the third class of the heat engine are mentioned clearly as reversed heat engine. The first type of reversed heat engine is refrigerator, while the second type of reversed heat engine is a heat pump. You are able to differentiate these things very clearly, right? This is quite inverse of this is the refrigerator. In case of refrigerator and a heat pump, the performance metrics are expressed in terms of coefficient of performance than that of calling that as an efficiency, right? So if it is coefficient of performance mentioned in the problem now, predominantly we are going to deal with two heat engines in the form of reversed heat engine. One is a refrigerator or a heat pump, right? Then you may have a question, what is Q1 and Q2? Heat supplied is Q1 and Q2 is heat rejected, right? So on understanding inverse of this is this. That is, as an output, we are expecting heat rejection by supplying some work into the system. Here we are waiting for the system to deliver work at the output. Here we are supplying some amount of work done at the input to reject some amount of heat. Yeah, we can able to understand this simply in case of our home refrigeration. What we are expecting at the output, we are expecting some heat rejection. If you are placing hot water inside the fridge now, or a normal conditioned water inside the fridge now, we are expecting the fridge to reject some amount of heat now by supplying some work into the system. Say, for example, we are supplying electricity to the refrigerator to remove some heat from the water what we kept inside, right? Similarly, the second class of reversed heat engine is heat pump. In case of heat pump, we expect the heat pump to supply some heat into the arena, right? So the key difference between this with this two is this is quite an inverse of the very first formula. While looking in a detailed manner, as I mentioned earlier, Q1 stands for heat rejection, Q2 stands for, sorry, Q1 stands for heat supplied, while Q2 stands for heat rejection, right? In case of refrigerator, we expecting heat rejection at the output, but as an inverse in case of heat pump, we are expecting heat to be supplied. In case of cold region, right, cold climatic region, we are using air condition, right, for supplying some heat to us, for supplying some reduced heat to us, right? Likewise, in case of cold region, those community expect some hot air to be supplied at its outlet, right? So for the supplied work done, for the supplied electricity, they expect some heat to be supplied at their room. That is the purpose of heat pump, right? Those differences are to be understand clearly, right? Difference between a conventional heat engine and the two classes of its reverse, one in the name of refrigerator and another one in the name of heat pump. While the key purpose of the refrigerator is to remove heat from the observation, while the purpose of heat pump is to supply heat for the provided work done, right? So this presents graphical illustration of the same for better understanding, right? So just imagine this 2D layout that this box is a hot reservoir which is of high temperature, capital T1, and this is of a cold reservoir which is capital T2, right? For heat engine, what the things are happening now, heat is some amount of heat is supplied to the heat engine, right? Then some amount of heat is getting rejected to the reservoir. On combusting petrol or diesel, right? On combusting petrol or diesel, we are having some amount of heat, right? We are supplying that heat towards the heat engine. Then on generating some amount of work done, heat engine rejects some heat at its outlet that has been sent to the cold reservoir, right? It is inverse in case of heat pump or a refrigerator. That is why we used to call this as a reversible heat engine, right? Yeah, here work is supplied to the system. You are able to witness, right? In case of heat engine, we are expecting this heat engine to perform work done, which is difference of Q1 minus Q2. Heat supplied minus heat rejected. Heat supplied is always greater than heat rejected here, right? We already witnessed the heat pump or a refrigerator were called as a reversed heat engine, where we are supplying work done into the forum, right? Here we are expecting, here we are expecting heat movement from bottom to top, right? So Q2 is being fetched into the heat pump, then it is extracted as Q1, right? Heat rejection must be happening in case of refrigerator or a heat pump. Just imagine we are placing a normal water in the fridge. We are expecting the heat to be removed from the vessel, right? From the water. Vessel consists of some water, right? So that is supplied towards hot reservoir. Let me present another form of success metrics, measure of success metrics of heat engine, as thermal efficiency of heat engine can be expressed as Q1 minus Q2 by Q1. Then coming to the success measure of refrigerator concern, Q2 by Q1 minus Q2. We all know why it has been written like this. Here, heat rejection is the objective, right? In case of heat pump, heat supplied is the objective. So Q1 divided by Q1 minus Q2. This constitutes mere inverse of heat engine, and it's been a modified form of the same, right? So this slide is very important in solving future network-based problems. So just I am forwarding you towards the next level. The next key topic is Clausius inequality. The Clausius inequality statements clearly highlighted that the cyclic integral of heat transfer divided by absolute temperature is always less than or equal to 0. When a system performs a reversible cycle, na, this less than or equal to is equal to 0 in case of reversible, and it is less than 0 in case of a non-reversible process, right? And it's been graphically illustrated as an example, while figure A represents first law of thermodynamics, while figure B represents second law of thermodynamics. Those discussions were presented here. The original system in figure A receives a small heat transfer from the source at a temperature capital T and produces some work called del W, right? The heat can be replaced by reversible heat engine. This del Q is replaced by an intermediate reversible heat engine operating between the system at temperature T and the standard temperature reservoir temperature T naught, right? Producing a work called del WR. This reversible substitution leads to the condition called Clausius inequality. Then you may have a question, what is meant by reversible substitution? Reversible substitution means replacing an equal actual heat transfer process with an equivalent reversible heat engine process. So without changing the overall effect of the system. This Clausius inequality is pretty important uh, in case of the second law applications, right? We will witness the same in case of future slides. Fine. So coming to the key difference between reversible and irreversible process, the same can be discussed in case of unit 1. Let me repeat again for better understanding because it comes under second law of thermodynamics as per our syllabus. That's why we are having a slide in between the condition. Reversible process that can be reversed so that both the system and the surrounding return exactly to their initial state with no net changes, right? While coming to irreversible process, a process that cannot be completely reversed. Say, for example, evaporation of a camphor can't be a reversible one, right? That constitutes an example for irreversible process. While in case of reversible process and irreversible process differences, we are having many examples in graphical form. Let me quickly move you towards next slide. You can infer this later while preparing for examination, right? This slide presents the very first cycle of thermodynamics and very important too. The cycle titled Carnot was first suggested by a French engineer, Sadi Carnot, in 1824, which works on reversible cycle, right? It consists of totally four processes. We all know cycle minimum need of three process at least, because only with the triangle we are able to constitute a process, right? We are able to form a process, right? Likewise, here we are having four processes, while process 1 to 2 governs represents isothermal expansion, 2 to 3 represents adiabatic expansion, 3 to 4 represents isothermal compression, while 4 to 1 represents adiabatic compression. This is for Carnot engine cycle, while it is inverse in case of Carnot heat pump or refrigerator cycle. Wherever the expansion is replaced by compression here, because we all know from the previous slide that refrigerator and heat pump are the reversed form of initial heat engine, right? The Carnot cycle understanding can be better with the example of this piston cylinder assembly movement, while T1 governs heat source and T2 governs sink, right? Those thermal efficiency, we already witnessed thermal efficiency of any system can be represented by ratio of work done to that of heat supplied. Work done can be written as Q1 minus Q2 divided by heat supplied by the source. Q1 is heat supplied and the Q2 is heat rejected, that we all know. With that, I am simplifying further on rearranging this equation in the form of 1 minus Q2 by Q1, which is equal to 1 minus T2 by T1, right? Where simply Q is equal to the general effective equation, Q is equal to mCp delta T. If it is in that form of 1 na mCp T1, if it is in the form of 2 na Q2 is equal to mCp T2, right? So this slide presents Carnot's theorem, where we are trying to understand cycle, Carnot cycle in a detailed manner. This Carnot theorem states that all engine operating between given constant temperature source and given constant temperature sink, none has a higher efficiency than a reversible engine. For a better understanding, please refer this nutshell. No heat engine operating between two given temperature reservoirs can have an efficiency greater than of a Carnot engine. reversible Carnot engine operating between the same reservoir. One thing you want to understand here, heat engine is different, Carnot engine is different. The formula what you had earlier, this is an example of heat engines. Anyhow, heat engine and Carnot engine are more or less equivalent, but the key difference between Carnot engine and heat engine is Carnot engine is only a theoretical engine, while heat engine is theoretical as well as the actual. While coming to the actual implementation of any theoretical concepts, we can't expect maximum performance as it is what we had in case of theoretical. So that is the key difference between this Carnot and key engine, right? So coming to this graphical representation concern, we are having two heat engines to understand this theorem. No heat engine operate between two given temperature reservoirs. These are all the two temperature reservoir, source T1 high temperature, source T2, which is sink, right? This is the mere extension of the diagram what we had here in this slide, right? The heat engine's graphical illustration. So no heat engine operating between two given temperature reservoirs can have the efficiency greater than that of reversible Carnot engine, right? So we are having two heat engine titled A and B, heat supplied to A, heat supplied to B, heat rejected by A, heat rejected to B, work done by A, work done by B. So this graphical illustration represents operating between same source and sink of which HEB is reversible. Now imagine the work done by HEB is reversed. Here we are having work done by the system. Here work is supplied to the system. And you may also witness HEB is written as EHP, that is a reversed form. Now HEB is reversed, right? So what we are trying to understand from here is no heat engine operating between two given temperature reservoirs can have an efficiency greater than that of a reversible Carnot engine operating between the same reservoir, right? Any number of heat engine, right, can't have an efficiency which is greater than that of this reversed Carnot engine, right? So that is the theme what we are having. Now we are clubbing both engines, reversed engine as well as the regular heat engine into a single diagram, right? Where we are able to understand, we are removing source T1 from this slide, from this illustration, as a mean of which we are having a common connection from a reversible heat engine towards heat engine A, while heat engine A regularly supplies delivering some work at the output. The same work is little bit used to be provided towards the reversible heat engine. Likewise, the Carnot theorem is getting stated. Also, simply you are able to understand reversible heat engines are greater in efficiency than that of a regular heat engine, right? Yeah, if heat engine is reversed now, it becomes Carnot engine, right? That is the theme of Carnot's theorem. Efficiency V is greater than or equal to efficiency A, right? While there is also a proposal for reversed Carnot or corollary Carnot theorem, where the researchers attempt efficiency of B is equal to efficiency of A. Its proposals are the efficiency of all reversible heat engine operating between the same temperature level is the same. This is the key difference between a regular Carnot theorem and its corollary, right? While in this slide, you are able to have some formulas in the form of reversible substitution, right? The general formula for refrigerator in the reversed manner is presented here. For the heat pump is presented here, and the efficiency, reversible efficiency of the heat engine is presented here. So try to understand. Let me repeat again. There exists a difference between Carnot engine and a heat engine. Any reversed heat engine can be called as Carnot engine, while a regular engine is simply a heat engine, right? So you are able to make use of this formula for future problem solving purpose. Now we are going to have some problems. What we are going to have in the form of a big question or a small question in case of our assessments, right? So the very first problem, A heat engine receives heat. Simply on inferring the terminology heat engine, you need to recollect the general graphical illustration what we had in the third slide or the fourth slide, right? In the heat engine receives heat at the rate of 1500 kilojoule per minute and gives an output of 8.2 kilowatt. We are in a situation to calculate thermal efficiency and the rate of heat rejection. On inferring this problem, we are being given with the two given data, that is receives heat at the rate, now it stands for QS, that is Q1, right? Gives an output of 8.2 kilowatt, the general output provided by a heat engine, right? That is work done. Now we are in a situation to calculate its thermal efficiency, followed by the rate of heat rejection stands for QR. So the graphical illustration of the provided problem is listed below. This is a mere modification of the graphical illustration what we had in the previous slide. For better understanding, I presented the key formulas of thermal efficiency, COP of refrigerator and COP of heat pump here on the slide. Simply, we are going to make use of this formula alone for solving this, right? So, this slide presents a solution for the same. As I mentioned earlier, we are having two inputs. One is Q1 and another one is W, right? Now, the value of Q1 is 1500 and its unit is kilojoule per minute. We are converting the same into kilojoule per second simply by dividing the value by 60. Also, we are converting the provided work output into kilojoule per second. Kilowatt is directly equal to kilojoule per second. That's why we are making use of the same, right? Then comes the thermal efficiency formula. W by Q1 simply 8.2 divided by 25, which gives you some value 0.328. On multiplying the same with 100, we are having 32.8 percentage. We have to understood that efficiency is unitless, right? For better standardization, we are multiplying the results of efficiency with 100 to have some value less than 100 percentage. A rate of heat rejection is very easy. We all witnessed W is equal to Q1 minus Q2, right? On rearranging that formula, we can have the value of Q2 as 16.8 kilojoule per second, right? I hope you are able to understand the problem, right? Likewise, you are also having a numerical problem, which is based on coefficient of performance and heat transfer rate in a condenser of a refrigerator. On inferring refrigerator, you need to make yourself comfortable with the second formula Q2 by W, and also you need to make yourself comfortable with the diagram what we had in the previous slide, right? So through problem number 2, you are going to deal with what? A condenser of a refrigerator based problem. So the formula Q2 by W is very much useful. So please look into this. Let me repeat again. Where in case of refrigerator, we used to expect heat rejection from the placed material within which, right? That is why the arrowheads are placed from bottom to top, where we are supplying work done for the heat removal to takes place. So simply here also only two given data sets are provided. By making use of this formula, you are able to arrive at what? The requirement of coefficient of performance and the heat transfer rate, right? Now, let me lead you towards the third problem, somewhat a complex one, but it is very easy to understand. This kind of problems where have the probability of getting questioned in case of 16-mark problem. Again, you are going to have a reversible heat engine that operates between two reservoirs. Just imagine a diagram what we had in the previous slides of heat engine, where the high temperature is 700 degrees Celsius and the low temperature is 50 degrees Celsius, right? The engine drives a reversible refrigerator. We also having a refrigerator connected to the output of the heat engine. Just imagine we are going to connect these two fellows together. We already have this uh, effect in the Carnot theorem also, but there exists a minor difference between the Carnot theorem and the third problem what we are discussing right now, right? Such refrigerators operating at a high temperature of 50 degrees Celsius and a low temperature of 25 degrees Celsius. In case of refrigerator, the high temperature is at the bottom and the low temperature is available at the top side. The heat transferred to the engine is, heat supplied to the engine is 2500, that is Q1 is 2500 kilojoule, and the net output of the combined engine refrigerator plant, the total W is 400 kilojoule. Now, with this, we are in a situation to determine heat transfer to the refrigerant and the net heat transfer to the reservoir at 50 degrees Celsius. Also to reconsider point 1 by obtaining efficiency of the heat engine and COP of the refrigerator, which is 45% of their maximum possible value. In order to score maximum, it's been your sole responsibility to convert uh, units accordingly, right? At first, try to identify the given data. Here, 1, 2, 3, 4, 5, 6, 7 number of data are given. It's been our responsibility to write the given data in a suitable manner. So, as we discussed earlier, temperature of the heat engine. Hot reservoir temperature of the heat engine is 700 degrees Celsius. On converting that into Kelvin, we are having this. Temperature of the sink of the heat engine is 50 degrees Celsius plus 273 is 323 Kelvin. Temperature of refrigerator, which is minus 25. The temperature of the sink of the refrigerator is not given. We are in a situation to find out the same. So the heat transfer to the heat engine, Q1 is given as I mentioned earlier, which is 2500 kilojoule. The net work output of the combined engineering refrigerator plant is W is equal to W1 minus W2. So, this slide presents a solution for the same. As we discussed, the two individual thermal representatives are being connected. That is, work done by the heat engine is utilized to run the refrigerator, right? So, please infer clearly from the diagram that high temperature is 700 degrees Celsius, right? While the temperature of sink of the heat engine as well as source of the refrigerator is same. That is why a common diagram has been drawn here, right? And we are having Q1 is equal to 2500 kilojoule. Q2 is to be find out Q3, which is a general formula, right? W is equal to Q1 minus Q2. Likewise, W is equal to Q3 minus Q4. On rearranging that equation, we can have an equation of this form, right? And Q4 is also yet to be found out. So, on solving this kind of problem, one can understand second law of thermodynamics much detailed than the previous case of simple problems. We all know efficiency, maximum efficiency. Efficiency is actually W by QS. The same efficiency for maximum in terms of temperature, now we can have T1 minus T2 by T1. On rearranging that T1 minus T2 at the numerator by T1 is 1 minus T2 by T1. This T2 and T1 are given. So the maximum thermal efficiency is 0.668. We all know efficiency is work done by heat supplied. W1 by Q1. W1 by Q1 can be equal with this, right? On transferring the denominator on the LHS into RHS, we can have the value of W1. Straight away, we can have the value of W1 here on simple substitution. We all know the formula for coefficient of performance of the refrigerator, right? From the previous slides, where we had a T2, T1 combination. Here we are having T1, T2 and a T3 combination. Here, the transfer happenings are between T2 and T3, while in case of previous demonstration, we had the transfers between T2 and T1. Here, the formula will be of T2 divided by T1 minus T2, while here, the formula is between T2 and T3 happening. That's why T3 by T2 minus T3 is equal to the coefficient of performance of the refrigerator can be obtained as 3.306. Then comes this is maximum actually. Whenever the term maximum is used now, we used to make use of formula in terms of temperature. While in case of a general COP, we are in a situation to express formula in terms of Q and W. Likewise, here in terms of efficiency also, we used to have W by Q. While coming to maximum efficiency, we'll have the right hand side in terms of temperature, right? Simply on rearranging this equation, we can have 3.306 as our, we are going to equate Q4 by W2 is equal to 3.306. On equating the available sources of equations, we are able to identify the rest of the things, right? So also heat rejection to the 50 degrees Celsius reservoir, which is our second thing to identify, that is 6298.6 kilojoule, right? Then, then coming to the second portion, reconsider the efficiency of the heat engine and COP of the refrigerator as 45% of the maximum possible value. So the efficiency now it's going to be rewritten in terms of 0.45 into efficiency max. This efficiency max is already available in the previous slide as 0.668. So on substituting this, we are able to identify efficiency value. W1 efficiency is equal to W1 by Q1. On rearranging this equation, W1 can be written as 750 kilojoule. Q is equal to W1 minus W2. On rearranging that equation, we are able to have W2. Now, COP formula what we had here now, that can be modified by multiplying it with 0.45. This is how we are going to have heat rejected at 50 degrees Celsius by assuming 45% of the maximum possible value. This kind of problem is very important in case of university assessment as well as regarding your gate preparation concern, right? Then comes the fourth problem. Two Carnot engine works in series. Again, a Carnot engine where two Carnot engine work in series between source and sink. Temperatures are given 550 Kelvin and 350 Kelvin. If both engine develops equal power, determine its intermediate temperature. This is the very uh, important problem where we are in a situation to identify its intermediate temperature. As of now, with the demonstration problem, we had discussion related to T1 and T2, or else T1, T2, T3, T4, right? Currently, we are in a situation to identify the intermediate temperature between source and the sink. The graphical illustration of the same has been presented here. While two Carnot engine work in series between source and sink temperature of 550 Kelvin and 350 Kelvin, if both engine develop equal power, determine the intermediate temperature. That's the question actually. So two heat engines connected in series, right? Source temperature is 550 Kelvin. This governs T1 and temperature between heat engine 1 and 2 is T2, right? And temperature between heat engine 2 and the sink is T3, right? Heat supplied by the source to the heat engine is Q1. Heat rejected by heat engine towards heat engine 2 is Q2. Heat rejected by heat engine 2 towards the sink is Q3, right? It's a very interesting problem. Now we are in a situation to identify this T2, right? While we all know efficiency formula in terms of 1, efficiency formula in terms of 2, also in terms of temperature, in terms of W by Q, we are able to recollect the basics, right? Simply on rearranging this equation from 1, as it mentioned earlier, we are just cross multiplying this form to have this, right? Then we are multiplying W with the T1 minus T2 divided by T1 and the Q2 with the T1 minus T2 and the T1. On rearranging this equation, we may have an equation of this nature. Simply on cancellation, we are going to have a key formula W is equal to Q2 T1 minus T2 by T2. From equation 2, rearrangement, likewise, we can have on doing this kind of wonders with the equation 2 cross multiplication, we may have another factor like this. Then on substitution of and the cancellation, we are able to obtain the intermediate temperature T2 as 450 Kelvin, right? So this is how the problems can be quoted or questioned in case of second law of thermodynamic application in case of thermal systems, namely, sorry, heat engine, refrigerator, and a heat pump, right? Then comes Clausius inequality. We all know the closed integral of which deals with ratio of change in heat transfer to the absolute temperature is always less than or equal to 0. from the previous slide, right? While if it is equal to zero, na, that is reversible. If the process is irreversible, na, that is always less than zero. So it's very interesting and a very easy problem to solve with based on Clausius inequality, where we are provided with 300 kilojoules of heat is supplied somewhat at a constant temperature of 290 degrees Celsius to heat engine. The heat rejection takes place at 8.5 degrees Celsius. The following results were obtained as follows. Classify which of the results report are reversible cycle and irreversible cycle or impossible results. For a small recollection, I am leading you towards the Clausius inequality slide what we had in case of our previous. Yeah, this is the concept of Clausius inequality. If this equation, if the cycle is reversible na, which is equal to zero, if it is reversible na, not reversible na, less than zero, right? So we are now going to deal with the problem based on these concepts, right? So based on the given data under the formula what we inferred from the previous slide, right? Heat supplied value is given as 290 degrees Celsius, right? Heat supplied at 290 degrees Celsius is 300 kilojoule per second. That is the given data. Heat rejected Q2 is 8.5 degrees Celsius, right? By applying Clausius inequality to the cycle or the process, what is provided here? We are just validating. We are identifying whether it is a reversible or irreversible process. Del Q is given in the problem. So this del Q is common for all the three cases, right? Divided by, in case of T concern, we are given with the constant 290 in case of degree Celsius. Even in case of previous problem, we converted a degree Celsius into what? Kelvin here, right? Likewise, even throughout second law of thermodynamics and wherever in case of thermodynamics, we are going to convert degree Celsius into Kelvin for better usage of SI units, better following of SI units, right? Likewise, we are going to have three cases of substitution. If the value is less than zero, na, then answer is irreversible. If the value is equal to zero, na, obviously it is reversible. Greater than zero, na, impossible, right? So there are three cases of Clausius inequality, whether it is irreversible, reversible, or impossible. So this kind of problems can be asked in case of medium mark questions, like a 10 mark or an 8 mark question. It's very easy to solve also. Then comes the last and final concept of this second law of thermodynamics, which is entropy, right? Entropy, we all discussed in the very first unit also. Sorry. Entropy is a measure of randomness of a molecule in a system. It is a function of a quantity of heat which shows possibility of conversion of that heat into work. In a nutshell, entropy may also be defined as the thermal property of a substance which remains constant when the substance is expanded or compressed adiabatically in a cylinder, right? Entropy, definitely it's a property of the system. For better understanding, we are having a minor derivation. Just you need to make use of this PV diagram where the initial state is governed by 1 and the final state is governed by represented by 2. The path followed by L, right? That is given in this form of arc, and the return of 2 towards initial state 1. This cycle is a reversible cycle because uh, the final state is trying to come back towards initial state while following a comeback trend. It is of two types. One is N and another one is M. Regarding this reversible cyclic process concern, we are having a small derivation. It's very easy for you to understand on your own. And anyhow, we are going to have a detailed discussion. We already had a detailed discussion in case of our classroom ambience. Make use of this fundamentals to solve this entropy, a property of a system, one among the key theorem in the second law of thermodynamics, right? Then comes the change of entropy in a reversible process. We all know del S governs the change of entropy. S2 minus S1 is equal to integral of state 1 to state 2, ratio of change in heat transfer divided by T. The closed suffix by R is the formula for change of entropy in a reversible process. It is a mere extension of the Clausius inequality statement. The next slide presents formula for change in entropy formula for the five key process what we witnessed in the very first unit. constant volume, constant pressure, isothermal, adiabatic, and polytropic process. Respective formulas were given. Please make use of this for solving problems in the forthcoming slide. There exist some characteristics of entropy also. It increases, that is, entropy increases when heat is supplied, irrespective of the fact whether the temperature changes or not. It remains unchanged in all adiabatic frictionless process. It increases if temperature of the heat is lowered without work being done as in throttling process, right? So with this fundamental, I am pushing you towards problem solving on the concepts of thermodynamics, right? Numerical problems on entropy. This is the very last slide or a stage, sorry, last stage of our second law of thermodynamics and its application, where we are given with an ideal gas is heated from the temperature of keeping in its volume constant. The gas is expanded back to its initial temperature according to the law PV power n. Sorry, a small typo happened here. If the entropy change into two processes are equal, find the value of n in terms of adiabatic index gamma, right? So this problem is very easy to solve on understanding our second problem. So let me lead you towards second problem straight away, right? A rigid cylinder containing 0.04 meter cube and 1 bar at 300 Kelvin is heated reversibly until the temperature becomes 400 Kelvin. Now we are in a situation to calculate Q1. Del S, assume nitrogen to be a perfect gas whose molecular mass is 28 and take gamma is equal to 1.4, right? So the given data are presented. V1 is equal to 0.004 meter cube, P1 is equal to 1 bar, T1 is equal to 300 Kelvin. All these are initial conditions. Also, the given problem presents exit conditions, final conditions. T2 is equal to 400 Kelvin, and sorry, molecular mass of nitrogen as 28, and also some gamma value, constant values to make use of. Once the gamma value is presented, now we are able to recollect our unit 1 problem solving fundamentals, right? Where we had the formula of this nature, right? Cv is equal to R by gamma minus 1, right? In order to find the value of gas constant R, right, we are having a formula called a general formula called R naught by M. R naught is constant, universal gas constant 8.314. R for nitrogen is attempted here. If you are going for calculation of R for oxygen, the formula is going to be the same. The molecular mass component alone varies, right? So the gas constant R for nitrogen is 0.297 kilogram per kilogram Kelvin. This formula you are very much familiar with. PV is equal to MRT. On rearranging the equation, we are going to have M is MS 0.00449 kilogram. By making use of this prerequisites, we are going to calculate QS, which is simply MCV del T, right? CV is also a constant and it's been calculated using this formula on supplying heat of 0.333 kilojoule. We are also in a situation to calculate the entropy change. Entropy change for what condition? It is for gamma condition, right? Yeah, for a polytropic condition. For a polytropic condition, we have to make use of this formula Cv n minus gamma divided by n minus 1 log E d2 by T1, right? It is clearly mentioned in the problem also. That's why we are making use of. You may have a confusion, right? Here we are struggling between gamma and polytropic. Gamma deals with reversible adiabatic and N stands for what? Polytropic. You may have a question to go with what kind of formula selection. Definitely, it's not a reversible adiabatic because change in entropy is zero there in a reversible adiabatic process. It is having some formula for the rest of the four cases, constant volume, pressure, isothermal, and polytropic process, right? That's why we are going to deal with polytropic process and on substitution of available M, CV, and T2 400, T1 300 Kelvin, we'll have the final result of this nature, right? With this, I am concluding Introduction. Yeah, actual introduction to second law of thermodynamics and its applications, right? In case of any query, you are open to call me or text me at any situation. Also, you are open to post your queries in comment forum, right? Thank you so much for attending this video with full patience. Goodbye.